Recording. Again, welcome to basically the last part of chapter 30. I'm hoping to get to the example today. Today is a heavy lab. It's going to be a very, very loaded lab. It's actually going to have two labs in once. It will have the RL lab, and that's also for doubles as the AC also lab. And we also will have the Rlc Circuit basically lab. Basically, we get into the resonance, which is technically part of chapter 31, but stuff that is covered in lab doesn't have to really be in sync with the lecture. Since you guys have a lot of time to prepare the lab report, by the time the lab report is going to be due, you guys are have covered the content for these things. So that's in a nutshell basically what we have to do today. The other thing also I need to remind you about is the fact that we have homework for chapter 30 that is due this Saturday. It's before the actual Thanksgiving break. The homework for chapter 31 is going to be immediately due after the Thanksgiving break, actually on Tuesday, which is a little bit different than what we normally do. Depending on how fast we go after the break for content for chapter 32, the last homework may be due on Saturday or maybe due on the Tuesday after, so that the focus then will become just the last exam 4 and also the final. So this is basically where we stand in terms of the content and assignments, okay? So that's in a nutshell everything that I have in here. Of course, you will have a last quiz also. There will be no more quizzes after quiz 4, which is going to cover chapters 30, 31, and 32. Okay? So, unless you guys have any question, I'm going to finish the chapter 30, the stuff that we started from chapter 30. I guess, let me first of all share the screen. So this is the things we did last time, basically. We talked about, we defined the mutual inductance, basically, when I have two coils influencing one another, because the primary coil, or coil number 1, could basically have since there is a current running through it, it's going to create its own magnetic field. And that magnetic field, of course, is going to vary with time, because the current is an alternating current, is changing current. If the current is fixed, it will generate a magnetic field still, but that magnetic field will not have its flux changing, okay? Since the flux is not changing, it's not going to induce a current in the secondary or an EMF in the secondary. So in order for me to really have this influence, basically, the induction of a current in the secondary, I have to have a current varying first in the first one. So that is basically in a nutshell what that was. We were able actually to find the mutual inductance. Basically, we had a definition of how that is related to the rate of the flux in the primary. Let me find what we did. Actually, first of all, we did some calculations for the magnetic field for different configurations that we needed. And we found the magnetic field created by a single, basically, loop. And then we generated that, we generalized that for as many loops as we can in this case. And we had an n number of them. We used actually Ampere's law to find what the magnetic field is. So it turns out it's related to the density of the packing, how many basically turns I'm going to make per unit length. So that's important. That the n is. Mu naught depends on the medium. Obviously, actually in practice, you don't use the vacuum as your medium in there. You use actually metals in there with high permeability to increase the magnetic field. So you would want the B to be as high as possible. So instead of using mu naught, you're going to use the Km, which is a relative, basically, permeability of the medium times mu naught. And of course, it has to do with the electric field. It's the electric field that creates a magnetic field. So we were able to find the magnetic field for a long solenoid. The reason why we said long solenoid is because when we applied Ampere's law in here, if you guys remember, we didn't really stretch this hypothetical or Amperian loop toward the end. Otherwise, the magnetic field will curl in a different fashion, and Ampere's law, Ampere's law would not apply that way. So it's going to give me some different answers in here. So as long as this solenoid is infinite, basically, is very, very long, then this is a result for the magnetic field is in here. Now it turns out that this expression is actually very useful, because even if compact region, you can still use it and you're going to get very, very good results. Similar to when we did the capacitor, we said, first of all, infinite plate. So we used the result of an infinite plate and we found the capacitance there. Same thing, same idea. But in practice, the capacitance is not really infinite. It's as long as the length side or the area size is much, much bigger than the separation, the gap between the two plates. The same thing in here, okay? As long as this length in here is very large, relatively speaking, compared to its own size. So it should apply, okay? So as long as you're not worried about the magnetic field toward the end, you're fine. So this result will hold true. Then we considered a different kind of solenoid, which has this donut shape, if you wish, solenoid, where you wrap the wire around it. And again, we found the expression is slightly different. Instead of having the density of the wires in there, namely n per unit length, we have as n over 2 pi r, where r is the radius in here, or the distance from the radius. So this is really not a constant. It depends on how far you are from the center of this toroid. So it really depends on that. So it's not really a constant. But again, as long as you're concerned about the center, you can use the average value between the inner radius and the outer radius. So that is basically the expression for the magnetic field. In other words, when you are very close from the inner radius, the magnetic field is stronger than when you move further away from it, okay? So this is an interesting result for that. So we found that. After we found that, we took the case, for example, for the actual stuff that we're supposed to be doing. I'm just reminding you guys of what we did so far. And we wrapped wire. So we really have a solenoid in here, in this wire. And then we took another wire in the secondary and we ran it where we want it in here. I said we take a number N1 for the primary and a number N2 for the secondary. It doesn't matter really, as long as they don't have to be necessarily equal. Now, the idea here is you run a current. So you have an EMF in here, okay, in the primary, and you run a current, and this current has to be changing with time. It cannot be fixed. As long as it changes with time, it creates, of course, a magnetic field by that expression that we just found, nu naught n times I, where n is just the number n1 divided by L. Then that magnetic field would change with time. As it changes with time, per Faraday's law, it's going to induce an EMF in the secondary. If I connect the wire, it's actually going to run a current in the secondary, okay? And that current also will be alternating current, okay? And we found that this relationship in here is can be expressed, can be idealized by an expression which we call the mutual inductance. So this is a transformer that I asked you guys to do, also part of the discussion. We define the mutual inductance as how much magnetic flux, basically, per loop, per turn, times, of course, the number of turns in here, is proportional to the current that causes this flux to change in the secondary. I could have defined it backward, is if I change the current in the secondary, how much change of flux overall in the primary. Of course, it's going to be the number of turns in the primary times the flux per unit per basically loop, okay? So this is actually, the mutual inductance has this expressions in here. It turns out, as I argued there, that there is actually both of the expressions are the same, and the mutual inductance is whether you look at it from one way or the other, it's the same. Mathematically, it's the same thing. So we found the mutual inductance for that shape, and that is the between two, basically primary and secondary, like in a transformer. But then we define the self-inductance as similar phenomenon, except that the wire will act on itself by itself, and we ended up with a similar expression, but now we have the inductance for that. So we were able to find the inductance, namely mu naught n squared, which is the number of turns divided the length of the solenoid times the area A, okay? We played a little bit. First of all, before we do that, we found the energy associated with building a current in an inductor. That energy turned out to be proportional to the square of the current, okay? Because you integrate, you sum from 0 to the finite value of the current, and you start from 0 current, and you're building up. So basically what an inductor is, it builds up energy in it, and what that energy has to do is with the current. Unlike the capacitor where you build energy by putting charges on it, and that is stationary, this one you build energy in it by adding actually current in it. So it's going to oppose to it. So basically now you have an amount of energy. How much energy is that? All you have to do is just integrate the expression of x dx between 0 and L and I, and you end up with this expression. So this is in joules. Then, in a similar fashion, that's what we did also for the capacitor. We expressed, again, the inductance that we just found for the inductor, the self-inductance, which is this expression. We replaced it by, in this expression, and then we isolated everything, and instead of dealing with the current, we dealt with the magnetic field. Remember, we have the magnetic field is proportional to the current. So it could replace the value of the current in terms of how much it is equal to, in terms of the magnetic field. Because what I wanted to know is how much this would be in terms of the magnetic field, because the current creates a magnetic field, so and it's proportional to it. So if I don't have a current but I have a magnetic field, it's the same thing. So the energy turned out to be proportional to the square of the magnetic field. All you have to do is sub the value of I with what we found, B, remember, equals to mu naught n times I. So isolate I by itself, and you have B over mu naught n, and you replace the expression. And now you have the energy in terms of the square of the magnetic field instead of the energy in terms of the current. This expression is important, by the way. That's why I put it in parentheses, if you guys remember. And then we noted that the L times A is nothing but the volume. So if we are interested in the energy density, namely how many joules per cubic meter, that would be just dividing by the volume, and it's this expression. This is similar to what we did when we did the capacitor, and we found the expression for the energy to be 1/2 of epsilon naught times E squared. So when you have an electric field, you have an energy per unit volume, which is given by this expression. Obviously, if I am not in a medium vacuum, I have to replace the permittivity of the medium with this expression. Same thing. If I have a magnetic field in a region in space, then I also have an energy per unit volume, and it's given by this expression. Again, if I don't have vacuum, I'm going to replace the permeability of the medium instead of that of the vacuum. So those expressions are very, very important, and I think this is where we left off last time. You guys remember this discussion? Yes? We have a big lab. I'm hoping really that the rest of the class will join us. Otherwise, they really have to watch the recording for it. Thank you, Daniel. Okay, so obviously this stuff is not easy, by the way. This is really probably some of the most advanced physics that you're going to have in terms of that involves math and involves a lot of things. I know you say relativity and quantum mechanics, but those really, they are not that hard in terms of their math. Okay. Anyway, so we're in business then. So let's see where we stand right now. We are interested in if I combine an R resistor and an inductor. First of all, I need to mention this from the get-go, that this is, now if I'm using circuits and I have an inductor in a circuit, this is how the inductor would look like. Oops, I'm supposed to draw here. Oh, what is my drawing tool? Grab a green wire. Okay, so this is how the inductor would look like. So this is an L for an inductor, no matter what shape it is, okay? When I did the calculation last time, I remember I did it for an infinite long solenoid. This would work the same thing for the donut-shaped solenoid, so it's not any different. As a matter of fact, if you open any electronic device, you will not see them infinite. You will see them curl around, and you use a metal, usually iron, to strengthen the magnetic field and have more effect in there. Okay, so this is an inductor. Remember, the resistor looks like this. So this is a resistor. I'm just now going through the list of what we have discovered. A capacitor would look like this. A battery would look like this. This is in any circuit in there that you see. Now, a power source that is not fixed, namely an AC source, looks like this. Usually, you need two things. So for this one, you need the EMF. For this one, you need the maximum voltage, V naught, and you need also the frequency or omega, or the angular frequency, one of the two, because it's varying. How often is it going to go up and down? So you need two things for this one. And then we discovered also switches. And those are on and off only, so that's a switch. What else do we need in here? So those are the devices we have discovered so far in this class. So the last one in the list is the inductor. The EMF, the change in voltage across it, this opposes change, of course, in the circuit. So there is a minus in here that I'm not going to write, di over dt. This is simply Ri, again, delta V. The delta V across the capacitor is nothing but Q over C. Okay. And the EMF in here is just the EMF by itself. This one is by itself, and so on and so forth. Now, we have to be extremely cautious when dealing with an inductor in a circuit. Okay. Warning big time, okay? Let me explain what the problem with this is. If you have a circuit, doesn't matter what it is, and you have an inductor in it, here is how the inductor would look like. So you have the rest of the circuit in here. And then you hit an inductor. The problem with the voltage in here, V, from this point to this point, so let's call this one, let's make the current fly going in this way. Of course, this will oppose a change in the current via the expression minus L di over dt. It doesn't like the current to change. It's like mass. When you push the mass, it doesn't like to gain velocity. When it has velocity, it does not like to lose it. So when you stop it, it's going to not like it. So whatever the current is, it wants to keep it the way it is. So if you want to increase it, it doesn't like that. If you want to decrease it, it doesn't like that. It wants to keep the current the same via that expression, basically, in a similar fashion to F equals to ma. So here is the problem. In here, basically, the law that governs it relies on the idea that the flux inside is changing. The flux of the magnetic field is changing, and the EMF in here is equal to basically minus d phi of the magnetic flux. Of course, will create an EMF, and this EMF is similar to that of an L. Are you guys hearing me? Because I'm receiving a message in here that says that there's something wrong. Is everything good?
It keeps breaking up.
Yeah, I don't know. Okay, so I will try to slow down, okay? So the problem with this one in here is that the circulation of the electric field that relates that basically gives this EMF is not equal to 0. It's actually equal to this expression itself. Okay. And this is, of course, a non-conservative field. Let me explain what that is. If I start from this point and I go through this path and come back in here, if I don't have any friction, it doesn't matter which path I have as long as I come back in here, the change in the potential, for example, for the electric potential or magnetic or the gravitational potential is 0 in this case, because my starting height and my ending height is the same. So therefore, if I go this way and come back in here, there should not be any circulation. I should have 0 change in, for example, if I want to know the gravitational potential energy of going from 1 meter high up to 3 meter high, and come back, it doesn't matter which path I do, come back to 1 meter high, the change in the energy, in this case, the gravitational energy, is going to be mg times the final height, which is 1, minus mg times the initial height, which is 1. So it's going to be 0. So that is the reason why the gravitational force derives from this potential, and the potential in that case is mgh. Okay. The same thing is for 1/2 of kx squared. That's also conserved quantity. The same thing actually for the electrostatic field for Coulomb's law. That is also actually conservative energy, conservative value. This one is clearly not 0, because this is circulation over closed path, and it's not 0. So in this case, really technically, I cannot apply the law of conservation, the second rule of Kirchhoff, to say that any path I take in here, it will give me basically the change of the potential equals to 0. Because if I take a point in here and go around and come back in here, I should find a potential that is 0. But the problem with that is I'm going through a non-conservative region in here when I hit the inductor. So the argument is the following, okay, to circumvent this issue. At any point, there is this non-conservative electric field in here, which gives you this EMF, which gives you this voltage drop. Okay, the charges will, the charges will move in such a way they will counterbalance this non-conservative electric field with an equivalent one that is actually conservative. So in other words, this non-conservative electrostatic field is the same as the one that the charges will do in such a way that they move and balance it. So in other words, ignore this whole thing and replace it by a device that is conservative. Okay, so this is the technique we're going to use. Therefore, we're going to recover Kirchhoff's rules. So that is the only word of caution that I'm going to give in here. Having said that, we're going to go to the RL circuits. So this is the RL circuit. So the first thing I'm going to do in this case is I have a DC power source. I have a battery, a normal battery that we've been dealing with. Of course, usually for good measure, we put a switch in here, S. And this is an EMF E. And in here, I have an inductor, L, and a resistor, R. And at t equal to 0, there was no current in the circuit. So that is the only condition that we have in here. And we want to know the current I at any given time later. So that is basically what we want to find, the current later on. So we're going to take Kirchhoff's rule, assuming the warning that you guys have seen works. Then I'm going to take a starting point. It doesn't matter where I'm going to start. So I'm going to start with this point in here, A in space. I'm going to follow the direction because this is where the battery is pointing. So this is a positive and this is a negative. So I'm going to follow the current in this direction. Once I hit this, because this is a switch is closed now, at t equal to 0, the switch has been closed. Now, the current will go through the resistor. So there is a drop in potential in here, normal drop in potential minus Ri. Normal opposition to the current change in here. Initially, this will not like the current to change, and this is how it doesn't like it, minus L di over dt. Okay, and then once I go from the negative side to the positive side, I actually have to rise in potential by an EMF and come back to the point A and back to 0. So this is basically the expression that we have for the voltage. So this is Kirchhoff's rule, really. Okay, and for the conservation of charge in here. No, I'm sorry, conservation of energy. Assuming that the energy is conserved, obviously I already made a warning in here that there is a problem, but that problem can be circumvented by thinking that there is some sort of, when the charges oppose that, they will actually displace because of this difference of potential in such a way that the electrostatic field that they create in their displacement is equal exactly to the non-electrostatic current, which is this non-electrostatic field that gives you this difference in potential, basically. So the two expressions are mathematically the same. So So having said that, then I'm going to solve this equation in here for the current I with this condition, that at t equal to 0, there was no current in the circuit. So if we do that, I'm going to basically move this expression to the other side, move this expression to the other side. So I'll be left with minus LdI over dt on one side is equal to, when I move this one to the other side, it's going to be Ri with a positive sign. When we move the EMF, it's going to be minus EMF. So what I do in this expression, usually, this is the technique everybody does, is get R out, and here divide by L also. So we're going to do that. Since everybody does this, we're going to do it. So we're going to be left with minus di over dt, and we'll be left with an R over L on this side, and we have an I minus E, the EMF over R, okay? Epsilon over R. So this is basically, in a nutshell, the expression that we're dealing with. The technique also in here usually calls for the substitution of variable, namely I prime equals to I minus the EMF over R. It's clear from this expression that di prime over dt is the same as di over dt, because this is a constant. The EMF is constant. Remember, I took a battery, a normal battery with a fixed voltage, so this voltage is not changing with time. So this voltage is like 10 volts or 20 volts, depending on what's going on. So having said that, then gives me the mathematical expression I'm left with is di prime over dt, because this is the second derivative, the first derivative with respect to time of the current. It's the same thing in here of di prime is equal to, again, R over L times I prime. The technique, usually you divide by di prime and you multiply by dt, and that's basically gives you, at the end of the day, this expression di prime over dt equals to minus, I'm moving the minus to the other side if you're curious, minus R over L times dt. I'm sorry, did I do this wrong? It's actually I prime. Again, all I have to do now is integrate. What is the integral of the left-hand side, anybody? Can anybody help in here? The integral. That's what we're trying to find in here, integrate. What's the integral in here? Of the left-hand side. Remember, we're integrating with respect to I prime. It's like integrating dx over x.
Would it just be ln x or ln I?
Does anybody agree with Faraz? Okay, so good. I think that's correct, yes. How about the right-hand side? Anybody else? We're integrating, R is constant, L is constant, and negative is constant. So that stuff will come out. We're just integrating dt now with respect to t.
So it's just going to be 2.
What did you say?
It should just be t.
Okay. Is that it, or is there something else, guys, is missing? Is that it, or we're missing something?
What are the bounds?
Else?
Are there supposed to be
Sorry?
bounds for this? Are there supposed to be bounds for this, or is it?
No. This is basically an indefinite integral. We're just finding an expression in here.
So plus c?
Are we missing something?
Plus
Does
c?
everybody agree with Farad? Is that what you said?
Oh, that's what
Plus,
seems. Yeah.
sorry?
Yeah, that's
Plus
what
300, plus 300,000 kilometers per second? Miles, that's correct? Plus 300,000 kilometers per second?
Wait, where did you get 300,000 kilometers per
C, the
second?
speed of light. C, the speed of light. Is that what you said?
No, I was just thinking about like integrals when like you have a indefinite integral, you just put C.
That's the only C I know. Oh, you mean constant. Okay. Okay, yeah. I want to see if everybody's following me, or am I going myself and C as a constant. Okay, good. Miles also seems to agree. So it's going to be a constant. So we're going to write it as a constant C. So usually, to avoid the confusion of myself, what I do in this case is constant. Okay, that's why I know it's not 300,000 kilometers per second. Okay, usually in here, what we do, we take the exponential of both sides. So this will just be I prime, and this will be equal to exponential of minus R over LT plus a constant, which is the exponential of a constant, which is going to be another constant. So this whole thing is going to be just another constant times the exponential. Not necessarily the same constant, but it doesn't matter. It's another constant. Now it's time to replace the value of I prime, because remember, I prime has to do with I minus the EMF over R. So this is actually I minus the EMF over R is equal to a constant times the exponential of minus T over tau L, where tau RL is simply equal to L over R. Okay, this is the time constant for the RL circuit. When we did the RC circuit, we found another similar expression, tau RC now. We didn't call it tau RC then, but we called it tau. So it was simply R times C. This is the time constant for the RC circuit. This is for the RL circuit. Remember, we had a capacitor and a resistor, and we ended up with an exponential growth of the charge. Okay. In this case, we're dealing with the current. So we really need to find what that constant is. So the current I then is equal to the EMF over R. I moved it to the other side, now it's positive, plus a constant times the exponential of minus T over this tau RL. Now, at T equal to 0, the current I of 0 is equal to 0. That means that 0 is equal to the EMF over R plus a constant. The reason why is that is because the exponential of 0 is 1. So which means that the constant all along is just minus epsilon over R, where epsilon is the EMF. So now we have found the answer to the current that we're supposed to find. So the current I as a function of time is epsilon over R, 1 minus exponential of minus T over tau RL. Let's say examine this expression. At T equal to 0, of course, I is equal to 0. This is how we started. 1 minus 1 is 0. Because the exponential of negative infinity is 0. So this is time. I know. I think there is an issue with the. Yeah. How is it now?
It's better at the moment. Yeah.
Okay. I don't know what's going on, really. Everything is turned off at home. I know. No TV, nothing. Unless my phone is causing this problem. Let me turn off the Wi-Fi on it. Okay. So at t equal to 0, there was no current in the circuit. And after infinity, the current basically went all and became equal to EMF over R. So initially, I is equal to 0, so the circuit looked like this. At t equal to 0, the circuit looks like this. So I have this one. This one now it's closed. So we are immediately after t equal to 0. And this one is like this now. So there was nothing in here. This is an open, like a broken. Nothing is in there. No current is flowing when you do that. But after a while, what is the voltage across the resistor? It's R times the current. This is I, by the way, as a function of time. So the voltage across the resistor will be R times this value, which is just the EMF. So all the voltage is actually inside there. So after a while, this is how the circuit then look like. This voltage, after it's a long time now, this is closed, look like this. So there is nothing in here. It's just a wire, straight out wire. Because the EMF here is epsilon. The current now, after a long time, okay, this is a long time. This is after t equal to 0, immediately. This one, the current is going to be epsilon over R, and the voltage across this one is going to be R times the current, which is simply the EMF. So the entire voltage drop is actually here, as if there is nothing in here at all. There is nothing anywhere in the circuit other than the resistor. So this is basically the technique in some of the problems that you will be facing and how to handle them when you have when they ask you and tell you, okay, immediately after the switch is closed, what happened? Then you can replace any inductor with an open circuit. Basically, you open it there. There is no current flowing through it. End of the story. And if they tell you after a long time, we have problem 59, which we're going to do together, where we're going to have that. We're going to find the similar situation. After a long time, then you just replace it by wire. That's it. This is opposite to what's happening in the case of the capacitor. The capacitor, immediately after you replace it by a wire, and after a long time, it's going to kill the current. So the capacitor will be an open circuit at the end after a long time. So this is opposite to what the capacitor does. So again, this is a current. It has this nice exponential growth from 0 to infinity. Okay, and then it stabilizes. It doesn't go any further. It does not like to change it. So this is one thing. Okay. Obviously, we could do the energetics, how much energy was consumed in the whole process. We can integrate from Li squared from 0 to infinity. And since I squared is just a constant, in this case, this expression basically, we're going to integrate it between 0 and infinity and find basically the energy in there, which we can do. And we find the energy also in the resistor, which is Ri squared, which is this expression. And we add the two, and they must be the energy that came from the EMF, which is just V times the current. And the V in this case is the EMF times the current, and the current is given by this expression. I'm not going to do this exercise because it's going to be a long one, and it's really it's important analysis that we need to do, because I have another circuit that we need to worry about, and that is the oscillator LC. Okay. Again, think of the following situation now. I'm going to have you imagine this for a second. We have this EMF. We have an AD switch. Okay. We have a capacitor. We have a resistor in here for the protection of the circuit in here. And we have an inductance. I'm not going to include any resistors in the second portion in here because I want to see what's going on. So initially, I have the switch. So this is B. Okay. This is where the switch is. So initially, the switch AB, so there is an E, sorry. So the switch in position A, and we wait a long, long time. So there will be a Q charge in here accumulating on this capacitor C. So this is, by the way, we're doing the LC now circuit, okay? And this is an inductor. So basically, there is a charge now that has built up after a long, long time, okay? And actually, we can find what that charge is. It's not hard to do. It's actually going to be C times the EMF. We did that. That's when we did the charging of the capacitor. So this is just an RC circuit, okay? Then, I'm sorry, the position of the switch was completely in the wrong direction. Oh, hold on. Okay, let me delete this part in here because I had it completely wrong. Okay, sorry. So this is actually the A. So this is which way the switch goes. Yes, it's still the same argument. Basically, when we are in position A this way, the switch, there will build up a charge in the capacitor, and the capacitor will be fully charged. So if you're curious how much charge it has, it's going to be C times epsilon. Okay, we did that when we did the RC circuit. But then we take the switch and throw it now into position B. Once we do that, this part of the circuit is completely isolated. So what we have in this situation, we have an LC circuit only, a capacitor, an inductor. And this 2 now, there is a charge now, Q naught, I'm going to call it Q naught, and minus Q naught in here. When we connect it this way, the charge tries to build up this on this direction. So there is a current that is going to start to flow through the inductor. That inductor will not like the change in the current, so it's going to oppose that and basically go through this direction in here. And at that point, we have basically decrease. So let's write the EMF. So there is a decrease of voltage in here because charge is being drained. And there is a buildup in the current in here inside the inductor. Once this is completely discharged, there is a current flowing through the circuit. Now this will not push any more current because it has no charge left in it. But this will not like the current to change, so it's going to continue pushing the current in the opposite direction and charges the capacitor in the opposite direction. And once the capacitor is charged, there will be a positive charge on this side and negative charge on the other side until this one runs out of energy and there will be no more current that it can push. Then in this situation, I have a charge that is sitting on this side positive, so the capacitor will push the current now in the opposite direction because it has energy, one half of Q squared over C. And again, it's going to go back and forth, just similar to the mass spring system. So let's write the equation in here for the second part, since we did already the RC circuit, which we're not going to. So assume that we have finished that cycle, and now we have a charge sitting on the capacitor Q naught, just when we switch the capacitor, the switch back to B. So at T equal to 0, the switch is equal to B, okay? Q is equal to Q naught, okay? And I is equal to 0. There is no current in this direction. There was a current on the other side, and that's also 0 because once this one is fully charged, that current also is 0. Okay? So, we want to know the current at any time in this portion now when we are at S equals to B, when the switch in the position B. So we have a current I. We have at any later time Q charge sitting on the capacitor, because it was Q naught, but it's going down less and less as a function of time. So we want to find this charge and we want to find this current. So that's basically what the problem is. So we're going to use Kirchhoff's rules. It doesn't matter where we start. We start at this point in here. Well, point B is fine. We go through point B. There is because the current is piling up in this direction, this does not allow the current to change. So there is a drop in voltage in here, minus L di over dt. That is from the get-go. Once we hit the capacitor, we're going to hit it from the negative side at this point, and it's going to be plus Q over C. And that's it. We're back to point B, so it's 0. This Q and I are related to one another because the rate at which the current is being depleted, the charge is being depleted, is I is equal to minus dQ over dt. So this is the rate of charge or discharge, if you wish. of the capacitor. Okay, so we're replacing this expression, and the minus times the minus is going to be positive, and the derivative of I with respect to t is going to be basically the second derivative of q with respect to time. Then we have this expression, L d second q with respect to time plus q over c is equal to 0. As a matter of fact, I'm going to divide by L both sides, and I will have the expression, the second derivative of q with respect to time plus q over LC is equal to 0. This is similar to when you did the mass spring system, when you said F equals to ma, m times the second derivative of x with respect to time, plus the constant of the spring times x is equal to 0. And you said, okay, if I divide by m, I will find the expression that second derivative of the position with respect to time plus k over m times x is equal to 0. The solution to this one, if you guys remember from physics 4a, was an oscillatory solution, a cosine of omega t plus phi, and where a and phi are given by the initial conditions, a and phi, by initial conditions at t equal to 0, and omega was equal to square root of k over m. In this case, omega squared is equal to 1 over LC. So this is the frequency. The solution, okay, hopefully it's back now. The solution q sub t now is going to be given by a constant times the cosine of omega t plus phi, where again the same thing, a and phi, are given by what happened at t equal to 0. Namely, q is equal to q naught. What was the initial conditions? Yeah, q naught, and I is equal to 0. There was no current in the circuit. So this is similar to that problem. Do you guys remember this problem from physics 4a? For the mass spring system? Yes? No? Yeah, that's basically in a nutshell what it was. It's a mass spring system. Basically, you have F equals to ma, mass attached to a spring, and you apply Newton's second law. Basically, this is what you had. Okay. So this is what you had, if you guys remember. You had the spring. The symbol for a spring is actually similar to that of the. And you have a mass. This is the constant k. You pull it out of its equilibrium with an initial position x naught in this case. Okay. Or you give it a kick, depending. In this case, and it's moving in this direction. So F equals to ma, m times a, and a is the second derivative of this, which is equal to the force in this case, minus k times x. Move this to the other side, and you have exactly the expression that I wrote above. I did not share with you the screen, did I? Here's the stuff that I was talking about here. You guys remember this problem now? Basically, you have a spring, a mass, and you write F equals to ma. This is ma. This is F, which is minus kx. And you move the kx to the other side, and you have this above. Let's ring a bell now. Bell, and instead of k, 1 over c. So that's why I'm doing that. Q sub 0, remember it's q naught, and this will be a cosine of phi, because c is equal to 0. And I need to find the current I How is it now?
Seems to be clear.
Sorry guys, I don't know what's going on really, honestly. Okay, anyway. So this is the expression at t equal to 0 for the charge. We need to find the current. Remember, the current I is equal to minus dq over dt. And minus dq over dt, the derivative of cosine is a minus sign times minus is going to be positive. So it's going to be a times omega times the sine of omega t plus phi. Okay. And I'm going to impose the condition at t equal to 0, I sub 0 is equal to 0. That means that a omega times sine of phi is equal to 0. Obviously, a cannot be 0. If a is equal to 0, that means the whole solution is 0. And that is not good. Omega cannot be 0 because it's equal to 1 over square root of LC. Okay? L is fixed and C is fixed. Now, what is left with this situation is phi is equal to 0. So phi is equal to 0. That's one thing. If we sub it in there, that means Q naught is equal to A. If we sub this expression back in here, because cosine of 0 is 1. So now we have found actually the charge Q at any time t. Being an oscillation, it changes with time oscillation in an oscillatory fashion, which is just Q naught times cosine of omega t. And the current, I, also changes with time in the same fashion. It's actually equal to Q naught times omega times sine of omega t. Remember, there is a minus in the definition in here for the current, because that's the current, the rate at which the current is being discharged. The biggest deal in here is that the charge and the current are, first of all, they're out of phase. As you can clearly see, one of them is cosine, the other one is sine. So this is time t. So this is either Q sub t or I sub t. I'm going to draw them with the same amplitude, although there is a rate of omega difference between them. So I'm going to draw the charge, the charge with a red. So these are two periods basically of this. Now, the current, so this is the charge Q, by the way. So this is Q naught. And this is a Q sub function of t. Let's draw it with a different amplitude. Let's assume omega is about half what the other one is. So this is basically so the current is actually going to be 0, then maxes when the other one drops to 0, actually maxes in here, and then drops to 0 when the other one mins, and then maxes in here again, okay? Then it's going to be 0 when the other one maxes. When the other one vanishes, the other one maxes, and then when the other one is min, the other one maxes, and so on and so forth, until we get back into here. So this is the current, which is the amplitude is Q naught times omega. And this is the current, whereas the first one is actually the charge in the circuit. Both of them, as you can clearly see, are oscillating with time, okay? And the characteristic oscillation, the period t is actually equal to 2 pi over omega, which is equal to 2 pi square root of LC. Because omega in this case is 1 over LC under the square root, okay? So this is basically how the circuit behavior and LC circuit behavior. So it's an oscillatory circuit similar to the mass spring system, okay? As a matter of fact, so now we did the LC, RC, and also RL, all of them, all three of them. The last circuit that we're going to consider now is actually an RLC circuit, okay? Which is part of the lab, by the way, okay? So when you take all three of them, you combine them, basically. RLC circuit. Okay. Obviously, we started with an initial current, with an initial charge in the capacitor. We could have done the problem differently. We could have put the inductor in here, and we could have put the. By the way, I mean that is actually would be very much also the same thing. We could have swapped this too. Okay, and there would be a finite current that we just found because that's an RL circuit. Okay, and we found this current will be an EMF over R at the end. Okay, and the problem will be the same. Then the initial condition will change. Instead of Q equal to 0 or Q naught, it's going to be 0 if the capacitor was sitting in here and has no charge in it. And the inductor will have a finite current, which is epsilon over R. Okay, so we could have done the problem differently, where we could have actually the inductor has a charge in it, and the inductor now, once we switch back into an AB switch, then in this situation is going to try to push the current in the same direction. So the inductor will push the charge actually in this way, and it's going to go back and forth. Okay. If you're curious about the energy, which is a very, very important problem that right now I'm actually ignoring a little bit, the energy in the capacitor, remember, it's 1/2 of Q squared over C, and the energy in the inductor is equal to 1/2 of Li squared. These two quantities must be equal to the initial energy in the circuit, and the initial energy in the circuit at equal to 0 was just in the capacitor in this situation, which was 1/2 of Q naught squared over C. It would be interesting to take this expression. So what we're going to do in here, we're going to take this expression. So I'm going to skip for right now the RLC circuit. I'm going to defer it because the discussion of the energy usually is very, very important. Okay. Oh man. Okay. So the energy in the capacitor at any time t, not t equal to 0, okay, is going to be 1/2 of Q naught squared over C times cosine squared of omega t. Okay. The energy in the capacitor, the energy in the inductor, UL, is going to be 1/2 of L times I squared times this expression squared, which is Q naught squared times omega squared times sine squared of omega t. So all I did was square this expression and multiply it by L. And the same thing, I squared this expression and divided by C. And of course, I have the 1/2 before them. Remember, omega squared is just 1 over LC. So this, I'm going to replace it with its own LC, with its own expression, and I will be left with basically the following expression for the half of Q naught squared over C times cosine squared of omega t. And the energy in the inductor is 1/2 of L times Q naught squared times 1 over LC times sine squared of omega t. Cancel the L from both sides. And this expression is 1/2 of Q naught squared T times sine squared of omega t, plus this expression also is 1/2 Q naught squared over C, because the L cancels. The L coming from the omega squared cancels. So I'll be left with 1/2 of Q naught squared over C times the sine squared of omega t. If I take this expression out from both sides, I will be left with cos squared plus sin squared, which is 1, no matter what time it is. So this is 1/2 of Q naught squared over C, which is the initial energy. Because initially we had only charge in the capacitor and no current. So all the energy was inside the capacitor. So the energy is conserved in here. So at some point, the energy is sitting in the capacitor and being pushed through the circuit by the capacitor. Later on, and when it's doing that, it's going that energy to the inductor, and that inductor is building up energy while this one is losing it. And vice versa, when this one has all of the energy and this one has none, the other one will switch it back now, is push the energy. So this is basically similar to the mass spring system and the example that we have in here, when the spring is fully stretched, all the energy is in the spring, and the mass is stationary. So in this case, all the energy is potential energy inside the spring. And then once the mass comes back to its original equilibrium position, at that point the spring is relaxed. It's not compressed or stretched. So in that situation, all the energy is actually kinetic energy inside the mass. So, and no potential energy. And the energy is back and forth between kinetic and potential. This is the same thing, except now I have a capacitor and I have actually an inductor, and the energy at some point, all of it is in the capacitor, and later on changes to an inductor, and vice versa. And any time the total energy is conserved. This is in an ideal situation where we don't have really a resistor. When we have resistors, when we have resistance, same thing in this case. When we don't also have viscosity, the problem is easy to deal with. It's exactly the same picture in here, and the energy is never lost. It's always equal to 1/2 of kx naught squared. Same thing in here. The energy is never lost. It's always equal to 1/2 of q naught squared over c. So this analogy can go very, very far. As a matter of fact, like I said before, I think last time, is that when we build circuits, L is equivalent to the mass. This is to do an analog circuit. The 1 over capacitance is equivalent to spring constant K, and the resistance is equivalent to the constant of the spring, the viscosity, and the EMF in this situation is equivalent to basically the force F0. Okay, and what else do we need? The displacement. X on this side. The displacement is equivalent to the charge Q, and the velocity is equivalent to the current. So this is mechanical system, and this is an electrical system. This analogy can be a lot useful. I mean, when you're trying to build an analog circuit, trying to analyze mechanical systems that are very hard to do in the real life. So you build a circuit and you start playing with it. Okay, we still have time, I think, to get some of the ideas from the RLC circuit going. And we're going to finish them in the lab, because the lab actually deals with this stuff too. So, RLC circuit. Chapter 31 deals mainly with RLC circuit too, to be honest with you, but it's going to be dealing it with not with a constant source. It's going to be dealing with it with an AC source. Okay, so this is the situation. We have an EMF. We have a switch, usually for safety. We have a resistor. We have an inductor. We have a capacitor, and they are all in series. At t equal to 0, the switch is thrown on in the on position. Okay. Initially, there was no current and no charge in the capacitor. Okay. So that's to make life a little easy for us. Obviously, if we apply Kirchhoff's rules in this case, it doesn't matter where we start. We can start from the switch and come back to it. There is a voltage drop in the resistor minus Ri. There is a resistance to the change in the current in here, which can be replaced by an electrostatic version of it, minus L di over dt. I forgot the L. And there is a drop in voltage in here, because there is a charge that starts to pile up in the capacitor. That is also minus Q over C. Once we hit the EMF, we're going to hit it in the positive direction, so there is a rise in potential by the EMF is equal to 0. Okay? So this is the expression that we're dealing with now. We're going to move everything with a minus to one side. The rate at which the charge is piling up in the capacitor is related to the current that is building this charge in it. So this is a positive. This is a charging, not a discharging. Okay, so it's a positive sign. So if we do that, we're going to have this expression in here. We need to find di over dt. Di over dt then is simply equal to d second of q with respect to time. And the expression can be expressed in terms of the charge. So this voltage first, usually the second higher derivative is first. L, second derivative of q with respect to time. I moved everything with a minus to the other side, so everything is going to be positive. Plus Ri, and Ri is R dq over dt plus Q over C is equal to, the EMF now is on this side, stays by itself, so it's going to be positive. So this is the expression that we have to deal with. What we usually do to get the answer for Q as a function of time and and I as a function of time is we divide by L, just like what we did when we did basically physics 4A. So when you divide by L, this expression will give me the second derivative of Q with respect to time, plus R over L dq with respect to time, plus Q over LC is equal to the EMF over L, okay? Normally, at this point, we're going to define the following value, okay? I'm going to define B as being R over 2L. And you will see the reason why the 2 there is because it makes the quadratic expression a little bit easier to deal with. I'm going to define omega naught, now not omega, as 1 over square root of LC. Basically, so that this expression now will have an omega naught squared. And this will be 2B, and this will stay as the EMF over L in this case, okay? So this will be the second derivative of Q with respect to time, plus 2B with this definition of dq with respect to time, plus omega naught squared Q is equal to the EMF over L. Now, of course, this omega naught is related to this one in here. Do you guys remember this from your physics 4A? Did you do something similar to this? Because we have to find the solution to this equation here. Did you have a discussion about this one in physics 4A? There are two behaviors. There's the decaying behavior all the time. How much of a decay depends on how much B and omega naught are related, depending on how much R and L and C are related to one another. There will be an exponential decay in all three cases. First case is when it's basically overly damped, namely the resistance is too big, namely the viscosity in the case of physics 4A was too high. So the system will go straight out and dies, basically, no matter how much voltage you have in there, because all of it is going to be wasted actually in the resistor. Or the resistance will be too low. It's going to, at the end, win, in a sense, it's going to dissipate the energy in of the system, but not as fast as it wanted to. In this case, the system can oscillate. So basically, it goes up and down and starts to oscillate until it damps to completely go down. And this is called damping, oscillations with damping. Of course, all of them will have the damped oscillation. And then there is a third case, which is usually the critical condition. And the critical condition, when both of them, they will cancel. Namely, there is a condition where we're actually off of that. So it's going to start going and then come down and also dies immediately too. But not like the first case, which was exponentially immediately the resistor will kill it. There's actually linear growth and then it dies away too. So those are the three cases. Do you guys remember this discussion from the physics 4A? When he did the mass, the spring, and also viscosity. Three things together. Anybody? It's fine if you don't remember it, but just I want to know if somebody remembers that. Okay. Anybody else? Okay, so let me have a refresher about that, okay, without going into too much math in it, because the math can be a little bit cumbersome and too long, and we probably are going to do it in the lab anyway. So, it's not probably, we're going to do it in the lab, okay? So let me explain now this expression. What happened in here? What happened to my stuff? Did it erase? Okay, good. So usually the technique, in a nutshell, what it is you say that there is a solution of the form Q sub t is some constant A plus some constant B times an exponential for the sake of argument, because I know it's going to decay in any matter. So it's going to be minus gamma t, okay? Since I know what Q is, I know what dQ is. My point in here is trying to find A and B, okay? Those are the two constants. Gamma also is another concern. We need to find it, okay? A and B will depend on the initial conditions. Actually, one of them will, okay? The other one is not. The other one is going to be dependent just on the EMF. This is called the steady state, and this is called the transient, and we're going to get into it a little bit. So dQ over dt, this is constant. So it's going to be just minus gamma times B times exponential of minus gamma t. The goal in here is find A and B in gamma. If I find them, I have found solution. That's basically what it is. So what I'm going to do now, assuming that there is a solution of this form, I'm going to take its derivative and see if it fits the plan. The second derivative of Q with respect to time, because I need it in here too, is going to be minus times minus is going to be plus gamma squared B exponential of minus gamma t. Now we're going to sub these expressions. This one involves just the exponentials. This one will not. This one will have omega naught in it squared. So what we have in this case is the second derivative is just gamma squared times B times exponential of minus gamma t plus 2B times minus gamma B. So it's minus 2B times gamma times capital B times exponential of minus gamma t plus omega naught squared times this whole thing. On one side, I'm going to multiply omega naught squared times B times exponential of minus gamma t. So I have omega naught squared times B times exponential of minus gamma t plus omega naught squared times A is equal to the other side was just the EMF over R. I mean, the EMF over L. Okay. So I subbed everything in here. I have some time dependency in here with the exponential. I'm going to make it equal to 0. And I'm going to equate this constant term with the other constant term. So A is already found in here. From this expression, we know what A is equal to the EMF over L times omega naught squared. Remember, omega naught squared is 1 over LC. So this is simply equal to omega naught squared. I'm sorry. Where is omega naught squared? It's going to be the EMF times C. Okay, we juggle the stuff in here where omega naught squared is, by definition, I defined it up there to being 1 over LC. So 1 over L cancels the L, and then you will have 1 over C, so it's going to come upstairs. So we found A. So this is easy. Now we're going to make this exponential times B equal to 0. Remember, every term of them have B exponential minus gamma t. B exponential minus gamma t, B exponential minus gamma t, this whole thing must be equal to 0. B cannot be to 0, because if it's 0, the whole thing is useless, because just there is no time in it then. So it's B times, what I'm left with the first term is gamma squared. So I'm going to replace gamma squared. What I'm left with in here is minus 2B times gamma. The B exponential is gone. And what I'm left with for the third term is omega squared naught. That's it. Must be equal to 0. As I said before, B cannot be equal to 0, otherwise we have a trivial solution. The exponential can never be equal to 0 anyway. So this is not equal to 0, so this must be equal to 0. So this is a quadratic equation in gamma only, which we need to find gamma also, in such a way that gamma is equal. That's what the advantage of putting the 2 there. If we do the 2, then the quadratic equation will have an easy solution. First of all, it's a minus times minus is going to be a positive. B plus or minus the square root of B squared minus omega naught squared. So I found actually 2 values for gamma. I have one with a positive sign and one with a negative sign. I wanted 1, I got 2. Okay, which is fine. So that means we actually have two solutions, possible solutions that fit the bill. Okay, I'm going to replace the final thing in here. Gamma. V, remember, was, I defined it on above there as being simply equal to R over 2L. So this will be R over 2L. R over 2L. Plus or minus the square root of, open parentheses. I promise this is the last. Okay. R over 2L again, squared, minus omega naught squared. I'm sorry, I know what omega naught squared also is, 1 over LC. So we have two gammas in here, one with a positive sign and one with a negative sign. The last thing that we need to determine, remember, to make this solution work was the letter B. The letter B will turn out to do with the initial conditions, okay? External excitation, which is the EMF, E, and the gammas, they satisfy this equation. Obviously, the square root can be positive, under the square, under the square root can be positive, in which case this whole solution is real, or it can be negative, in which case this whole solution becomes imaginary. It turns out that the imaginary solution will be more interesting than the real solution, okay? So this is the gammas that we have found. Okay, normally people, the way they write it is, okay, let me leave it as such, because sometimes the literature can be a little bit confusing. Here is the deal. If R over 2L squared is more than 1 over LC, in this case we have a real solution. Real solutions. And these two real solutions are both of them positive, because the positive is positive. We don't have a problem with it. The negative also, with the negative sign, also is positive, because R over 2L is more than the square root, no matter what happened, because you have R over 2L squared minus something, and you square it, you square root it. So both solutions are positive. So both the gamma with the plus sign and the gamma with the negative sign are both real and positive. Real positives. And each one of them, because I have an exponential of minus gamma to the solution, then will decay exponentially. So this is how this behavior works. So in this situation, the charge Q and time t will start from not zero, actually, because of this finite expression in here, okay? Because I really have to plug back into the expression. Remember, I have A plus something. So it's going to start from A, which is C over epsilon naught, and will basically is killed, because the resistor will kill the energy in there, okay? Now, there is another condition where actually R squared over 2L, the whole thing squared, by the way, is actually equal to 1 over LC. In this situation, the square root is 0. This square root is 0, because square root of 0 is 0. And of course, gamma, in this situation, I have two solutions, okay? Both of them are the same solution. So the solution actually will also, so this is called the overly damped. In this situation, actually, this is what happened to the current. It starts to grow and then go down. I mean, to the charge. Starts to grow linearly and then come down also. So this is critical damping. The final solution, where R over L2 squared is actually less than the other one, R over 2L squared is less than 1 over LC. This is an imaginary solution. And the imaginary, the exponential of the imaginary is going to be an oscillatory, up and down. What time do we normally finish? At 2:10? 2:10? Okay, give me about 3 minutes and I will make this point and I will be done with you guys. So, exponential, so in this case, it's going to have a real part, which is this exponential of minus R over 2L. What is the, this is, says real, but then I have in here an imaginary number. So the imaginary number becomes an oscillatory behavior. And in this situation, this exponential will be killed by the exponential of minus gamma, because the real part will have this term in it. So it's still going to die, but not as fast as the previous ones. As a matter of fact, it's going to oscillate in this fashion. Okay. So first of all, there is the envelope will be this exponential decay of exponential. So this is the exponential of minus r over 2 LT. But the behavior in here will be something like this. Again, the resistor will kill everything at the end of the day, okay? Sorry, I probably drew it a little bit. It's going to be shifted, always shifted by that term in here, okay? Sorry, there is a term that is going to shift things, which is this A. I was focused only on the transient behavior. So this is just the transient, okay? The transient is just this part, not the constants. What is it? Not this A. The A is actually the steady state. Okay, we still have a couple of minutes. I'm not going to really get. I'm going to promise to have more discussion in the lab about transient and the steady state. And that's going to be our discussion point for this chapters, okay? How do you find this stuff? Good? Okay. Usually there's a lot of stuff to be done in here, and we should be able to get the lab today. I gave you the instructions and everything, hopefully to get things done. There are 2 labs in 1 lab today, and we will meet in at 2:30, so we still have about 20 minutes. Okay, guys? See you in a little bit.
Professor?